One type of event is something we called a complementary event. And so the complement of an event is just the complete opposite of the event, meaning it just means that the event E doesn't happen. Okay, and the notation we use is this here, E with a bar over it. Sometimes you'll also see E with a superscript of C for the complement of E. But we're going to focus on this one here, and we would just read this as E complement. So there's a nice rule for complementary events, and that is that the probability of E complement is equal to 1 minus the probability of E. So let's put that into practice here. If you pull a random card from a deck of playing cards, what is the probability that it is not a heart? Okay, so probability of not a heart. Okay. Well, this is a complement. This is the probability of, okay, the opposite of heart, meaning not heart. Okay, so we can use our rule. This is 1 minus the probability of a heart. Okay, so 1 minus, and then the probability of a heart. Well, there are 13 hearts in the deck, and there are 52 cards. So this is 1 minus 1/4, or 3/4. Another relationship that can exist between events is what are called independent events. And independent events are when the probability of one event occurring is the same whether or not the other event has occurred. Okay. So for example, well, let's look at this example here. We'll determine if these are independent. So a fair coin is tossed 2 times. The 2 events are 1, the first toss is a head, and 2, the second toss is a head. So we need to know, if I know that the first toss was a head, is that going to change what I think the probability of the second being a head is? Another way of thinking about it is, well, is the first flip being a head going to influence the second toss? And, well, no, it's not going to influence. It doesn't really matter what the first toss is. The second is completely independent. So these are independent events. Independent events. Okay. All right, this next one, 2 events. 1, it will snow tomorrow in Holiday, and 2, it will snow tomorrow in Cottonwood Heights. This is not a city near Houston. I changed that for my video, so forget about that. We know where Cottonwood Heights is. It's very close to Holiday. Okay, so ask yourself, if you know that it's going to snow tomorrow in Holiday, would that change what you think the likelihood of it snowing in Cottonwood Heights would be? And the answer is yes. Okay, because they're so close to each other, we do believe that the weather would be pretty similar. And so these are not independent. Not independent. Okay, the next one, if you draw a card from a deck and then draw a second card without replacing the first, okay, are the 2 outcomes of these cards independent or not? Well, if we draw a card from the deck and then we draw a second card without replacing the first, that means that we know our second card can't be what the first is. And so certainly the outcome of the second card is going to be influenced by what the outcome of the first was. And so these are not independent. The reason we care about whether or not events are independent is because we have a special rule for independent events. So if we have 2 events, A and B, being independent, then the probability of both occurring, the probability of A and B, is equal to the probability of A times the probability of B. This is only if they are independent events. So let's look at an example. In your drawer, you have 10 pairs of socks, 6 of which are white, and 7 t-shirts, 3 of which are white. If you randomly reach in and pull out a pair of socks and a t-shirt, what is the probability that both are white? So because what we're looking for here is the probability of white socks and a white t-shirt. White t-shirt. Okay, so we've got this word and in there. So when we see and, that means we need to know if the events are independent. So the question is, if I pull white socks, is that going to change my probability of pulling a white t-shirt? Well, no. So these are independent events. This means that this is going to be the probability of pulling out white socks times the probability of pulling out a white t-shirt. All right? So the probability of pulling white socks. The number of ways we can pull out a white pair of socks is 6 divided by the total number of pairs of socks, which is 10, and then times, for the probability of pulling out a white t-shirt, is the number of ways we can pull a white t-shirt is 3, and then divided by the total number of t-shirts, which is 7. Okay, so now we go ahead and multiply these. That's 18 over 70, or 9 out of 35. Another example. A card is pulled from a deck of cards and noted. The card is then replaced, the deck is shuffled, and a second card is removed and noted. What is the probability that both cards are aces? So here we want two things to happen. We've got the probability of the first card is an ace, and the second card is an ace. Okay, so we've got this word and. That means we want to know, are these events independent? If they were not independent, there's a different rule that we'll learn here in a minute. But if they are independent, then we know this is just the product of the two probabilities. So the key here is that when we take the first card, right after it, we replace it and then shuffle the deck. And so we don't really think that's going to influence our second draw. So this is going to be the product of the two probabilities. The probability that the first card is an ace times the probability that the second card is an ace. All right, so, well, the first card that we draw, we want to know how many ways can we draw an ace, and that's 4 out of the total number of ways we could draw a card, which is there's 52 cards. Okay, and then times. For our second card, we've replaced that first card, and so nothing's changed. We're just kind of doing the same exact thing. And so, again, there's 4 ways we can draw an ace, and then 52 total cards. So this is 1/13 times 1/13. So that's 1 out of 169.